Hello, everybody. I hope we all had a good lunch. We are project 2, and our project is on developing edge AI applications for human robotic collaboration and Lego assembly operations. My name is Kayla.
Good afternoon, everyone. I'm Joaquin Snowden.
Good afternoon, I'm Toluwani, Olasoko.
And I'm Abdulahi. Okay, so our project is primarily going to be us using a Linux-based AI computer and a robot arm to automate detect Lego pieces and help us in Lego assembly operations in general.
The problem we're trying to address is automation, and it's a challenging task due to different shapes of Lego pieces, the sizes, and the orientation.
The techniques used in this project can be applied to industrial automation and smart manufacturing.
So our main project objective is just to see if we can train an AI model so it can accurately detect Lego pieces, but also be able to assemble those Lego pieces. And now this moves on to our research question. Would real-time object detection with a camera and Lego brick assembling with a robotic arm be a step forward in bridging the gap between computer vision and edge AI applications?
Our group hypothesizes that integrating computer vision and edge AI with a robotic arm can lead us to accurate real-time detection of Lego bricks from the
And for our expected contributions, we expect to improve existing edge AI by using YOLO to help detect Lego pieces more accurately.
Okay, so by the end of this program, we want our research paper to be one of the baselines and one of the performances that are going to be looked at for by performers or by researchers just for project that requires edge AI computers or robot arm or robot control system development.
And I'll be taking the brief literature review. As AI has been evolving, computer vision helps humans to mimic human visual intelligence. And as a team, we reviewed lots of research papers and I'll be going over a few of them today. First, we improved the V4 for grid detection in complex outdoor backgrounds with different lighting conditions, and resulted in a 92% precision. And we developed a lightweight level model for detecting apples in different lighting conditions and background conditions, and resulted in a 92% result.
Now, in doing these literature reviews, we saw the common pipeline, first beginning with collecting their data set, collecting their images, whether it was with pre-made data sets with a software like Kaggle, or if they were actually collecting the images on their own. One of the research papers actually used an iPhone 11 to collect 7,000 images. It always began with finding their data set. And then moving on to labeling, whether that was with the labeling that was already inputted into YOLO, or if that was using softwares like LabelMe or CVAT.ai so they can customize the objects that are in those images. They would always then label those images. Then, depending on whatever YOLO model they would like to use, then it's time to train those YOLO models. And then they will move on to the evaluation steps with something called performance metrics, which will get mentioned a little bit later in the slide, to really figure out why this YOLO model was the chosen one. Then they moved on to a simulation process, usually just with whatever software they are going to use just to see how well those YOLO models really did and what they're trying to research. And then there was possibly sometimes where they would deploy their training into actual hardware. And then another small key takeaway from those researches was that lightweight YOLO models basically showed that they can only be used for computer sources that were pretty limited in power. Now moving on to one of the limitations of those prior researches. As I mentioned before, some of those researchers only got to the simulation part when we know now, and for our project, we are actually deploying those models onto an actual robotic arm. And then another limitation was that they were just more relying on controlled environment. What do I mean by that? There were some research papers on electrical vehicle charging ports, bottle caps, kitchen utensils, where it was just about, is this a kitchen utensil or is it not a kitchen utensil? Is it a bottle cap or is it not a bottle cap? But in our case, we are not just training our model to say, is this a Lego piece or not, but it's training our model so it can determine whether it's a 2x2 piece, 2x4 piece. There's multiple Lego pieces just in general, but we are changing on a 200 different Lego pieces, and that's what we're trying to find.
Okay, so Of the research papers we read, we noticed that a lot of them use hardware that has high computational power. So our research was primarily focused on, optimizing the model we're going to use to be able to be efficient on both low computing end and a high computing end. In the sense that even if you have a low end device, you'll still be able to optimize your model and get efficient result. That's one of the things our research was primarily focused on.
And our research gap consists of bridging the gap between object detection using LEGO images, YOLO algorithm, and hardware assembly.
Then providing assembly steps for real-time LEGO detection and robot automation using YOLO algorithm.
Okay, so here is the flow chart of our study, and this is the pipeline of how this research went. So I'll start off by saying this is a supervised machine learning model. What does that mean? This basically means a supervised machine learning model is basically a model that has its data set labeled already. And then once take note of the computer vision algorithm we're going to use, and that's YOLO. So YOLO is a deep learning computer vision algorithm that helps the robots run seeds and then just computer vision algorithm in general. So we started off by getting 2,000 labeled images from Kaggle, and then we made sure that they were all labeled because we're using YOLO, and YOLO only works with labeled data set.
I think getting the 2,000 images data set, we were in XML file format, but YOLO can't read XML files, so we had to convert them to TXT files,
Okay, so one really important thing in machine learning is to avoid things like overfitting the model, to make sure the model is generalized and to avoid data leakage. And this was the reason why we had to partition our data set. So we made 70% of our data set for the training, we have 15% of it for the testing, and then we have 15% of it for the validation. So we want to avoid data leakage in the sense that we don't want the model to see what is not supposed to see while it's training. This way, it's not going to give us wrong results. And then we don't want the model to overfill, in the sense that we don't want it to confidently memorize the pattern, confidently memorize the images in the training, rather than memorizing the pattern in it. And then want to generalize the model in real world situations, because in real world situations, from the data set, it's not always the lighting conditions that are there. It's not the same shadows that are going to be out there. And then the lighting conditions can make the level piece appear differently. So that's why we want to make sure the model is able to perform real good in a real world situation. So we have to partition the data so it's gonna be generalized significantly.
Now moving on to the choice when it came to our methodology. So based off those previous research papers, we noticed that there was 5 different YOLO architectures that stood out. That being YOLO V8, YOLO V8 V2, YOLO 11, YOLO 26, and YOLO 26 V2. And we chose those 5, and then we did across 5 different scaling variants as well, being nano, small, medium, large, and extra large, making a total of 25 different YOLO models. And we trained those across 200 epochs. What is an epoch? That's basically just how many times the computer goes through its training. So as Abdulahi mentioned, that was 70%, and that being 1,400 images was going through each epoch. And as we are going to see in a graph later, we'll notice that each time it went through an epoch, the precision in those metrics have increased. And now we have 25 models. So then the question is, how do you really determine which model is the best? Just as you would try to choose which team would win a specific sports game or a tournament or something like that, you're going to look at the stat. And for YOLO object detection, it's called performance metrics. And I'm going to talk about 4 of the most important ones for us. That is beginning with precision. Precision answers the question, out of everything that our computer detected, what did it actually get right? And that is given by an equation of true positive over true positive plus false positive. Now, where do those 2 values come from? Those 2 values come from another performance metric called intersection over union, or IOU. And what is that? Basically, that is about how the computer matches with what the human eye sees, being the ground truth. And when it comes to YOLO, when it finds a particular object, it's going to surround it with a bounding box. And also for YOLO, it has a threshold that's already implemented in it, and that is being 0.5. So what does that mean? So the computer matches 50% of the ground truth. That is what's considered a true positive. So positive meaning that the computer found something, and true meaning that humans are saying, yes, that is the right image. But in the other case, if it's 49% or less, that's when it's considered a false positive, because it's positive, the computer said it found something, but I'm telling the computer, no, you're wrong, that is false, that is not what I asked for. Now, the next metric that was important to us is recall. Recall answers the question, out of everything that the computer found, how many objects did it miss that I asked for? And that is given by the equation of true positive over true positive plus false negative. Now, what is the value of false negative? False negative is when computer says, hey, I did not find this particular Lego piece, but I say, no, you are wrong. The Lego piece is right there. And just for a quick example, if there's 5 yellow Lego pieces there, and the computer only finds 4 of those Lego pieces, that is considered 80% recall. Now, the last metric I'll talk about, which is one of the most important ones for us, is F1 score. F1 score, I think about it as like the head coach, while precision is the offensive coordinator and the recall the defensive coordinator. It's making sure that they're both playing their roles. And why that's important in our project is because if we're ultimately trying to get a robotic arm to be able to build a full structure without having to stop or anything, we don't want the case where it's a low recall and high precision, because yes, it's finding the correct Lego pieces, but it's not finding all the Lego pieces. And then vice versa. We don't want a high recall and low precision, because high recall means, yes, it might be finding all the Lego pieces, but those Lego pieces that's detecting might be false positives, which means it's going to just be trying to build whatever structure it wants that I didn't ask for. And something else we kind of took into consideration is the speed. The speed sometimes, or usually just correlated to how fast the robot arm will also be able to know which model it's using, so it can actually pick up those particular Lego pieces.
Our best model was selected on who had the highest PR and MAP, meaning precision recall and mean average precision, and who was the fastest based on training.
And for our model deployment, we sent our best PT file, which was the best model we trained, to our AGI supercomputer. And then we imported that file into a 500 plus robotic arm code.
And for the robot arm pickup, this is the main part of the thing. This is where we're actually seeing what the model is doing. So after sending the model to the AGI computer, now the camera takes a picture of the Lego pieces it's been detected, and then it references to a QR code for its base location and to know the real world distance. And then that moves the robot's arm to exactly where the Lego piece is. It rotates its arm, it rotates orientation, and it goes exactly to where the Lego piece is picking up. Okay, so for our primary results, here are some of the primary findings we had. So after training the 25 models, as Joaquin said, we noticed that YOLO 11 in general had the best result, and it was better than the P2 architecture that we trained, which was YOLO P2 and 26 P2. And yeah, P2 was supposed to be, P2 is known to be good for small object detection because it still retains a lot of details you see in the picture, and it doesn't lose it during like the deep neural network downsampling, right? So that's why we know P2 is supposed to be the good one. Other models, while they are downsampling, they use P3, P4, P5, and this makes the model lose the details. So P2 was supposed to is known to be good for small objects, but in our research, YOLO 11 in general was the best.
Then specifically, YOLO 11S was able to reach a recall of 95%, training with our V13 Lego data set, which was the top 30 Lego classes that performed the best. And there you can see a table with the top 7 models that performed the best, and you can see YOLO 11 is the top 3.
And then, as I mentioned before, when talking about performance metrics, if you look at the graph in the bottom right, that's just comparing basically all 25 of our YOLO models based just on precision. So we could actually just see, okay, which models have the best precision for any problem.
And then for results, the mean of our results, so far YOLO 11 has emerged as the best for real-time Lego detection and automation with our robot arm.
In regards to our research question has been answered in our hypothesis with sufficient support.
Okay, so one of the most important insights we took from this project is that the YOLO model you're deploying on your AGI computer is highly dependent on the AGI computer itself. In a sense that even if YOLO 11 architecture was the best overall, 11 was obviously going to have much more accuracy than 11 small, right? That's the variant. But then looking at the accuracy, is not going to be the only factor we're looking at in deploying the model. There are other things we can trade off, like, we're looking at the accuracy, and then we also have to look at the time it's going to take for it to load in the AGI computer. We also have to look at the time it's going to take for it to load in the AGI computer, and computational power and memory is going to take for it. So those are all the factors we consider, picking the YOLO model we had on our AGI computer, which was 11 small.
And Abdullah already touched upon it a little bit, but one of our unexpected findings was that YOLO P2 architecture being one of our worst models actually. And usually from the research paper, it said that was the best at detecting small objects, but we probably have to look more in consideration of like the data set quality, and maybe P2 isn't the best when it comes to classification as well.
For comparison with prior research, our results align with and extended existing research by using YOLO or robotic arm to automate data assembly.
So here's a quick demo video for the results. So you see a queue that shows all of the local facilities, and then that's the QR code access the place location, just so the robots are able to know the location and the distance between the QR code and the local pieces we find there. And that's the robots on. And then this picks it up based on how you see it, and it rotates on the rotation. Like so. So here are some of the challenges we faced in building the project.
So one of the major challenges was that our computer just kept maxing out its memory. So what does that mean? Basically, it was crashing. And the effect on the project just means, okay, if the memory is maxing and the computer is crashing, that is delaying our training. Because as I mentioned earlier, we are training large and extra large models, and we're training that across 200 epochs. That might take a full day. So when it crashed at like 100 epoch, we then had to start over. But how we adapted is that we ended up just finding a code where it's able to pause and resume. And how we find that is that when we're training a model and we look in our files, there's a folder called wait, and it has two zip files called best.pt and last.pt. So we would copy the path of that last.pt file. So basically the training can resume where it stopped at.
Yeah, for our second challenge, it was robotic issues, coding errors, and coordination problems. And the effect on our project was wrong coordinates, meant wrong movement of our robot arm, and it led to the robot arm either picking a wrong piece or picking nothing at all. And the solution to this problem, we incorporated large language model to learn our robot code with better understanding.
Okay, so another problem we had was the inconsistencies in detecting the level pieces, and this was because of the lighting conditions, the shadows, the orientation, and now the level pieces were itself. So if we have inconsistency, that means the model is not reliable, so we cannot deploy the model. So the solution we had to do was to make sure we convert the RGB images to SSD, which looks at the hue saturation of value. So that covers up for the shadows and stuff like that, makes the accuracy increase in general.
So one of our limitations is that we did have to move to a selective subset for the Legos. So what does that mean? So basically when we were training, we decided to find the top 30 Lego pieces, but unfortunately in the lab, we actually didn't have those Lego pieces. So we have to just use the common pieces, such as like the 2x2, 4x2, and whatever else we just had in the area. And then another limitation was the Lego class detecting confusion. Sometimes it still couldn't understand like a difference between piece that had the same amount of rows and columns, but it had a different height. But that is something that we'll talk about how we can change that in our future work.
Now, we believe that our results would work in other locations, especially in a place like Lego World. For a different data set, it would depend on the similarity of Lego pieces, quality, label.
Okay, for the variation of fairness, a model, one important thing to note is that a model is only as good as the data that was fed to it. So as Joaquin said, we had our model, but we were not able to accurately, detect test performance because we did not have all of the level pieces there. And then another limitation we had was that we got like pre-labeled data set from Kaggle because there could be some bias in labeling it because of different lighting conditions and different class booking and stuff like that. So that's one of the bias we have in this project. So for the conclusion of future work, after this project, we were able to see that we were able to combine a computer with a robot arm and a camera to be able to assist with the Lego assembly operations by detecting Lego pieces and assembling it as we want it to be.
This experiment showed that efficient computer vision can support automated robotic tasks without relying on cloud computing.
We were also able to understand that it's important for individuals to train multiple models to measure performance throughout all the models trained.
And our future work contains maybe creating a YOLO model so we can actually use the full B200 Lego data set. As I mentioned earlier, we have to switch to a B30 data Lego set so we can get the better results. And then just updating that training set. So now, like I mentioned, the limitation where it couldn't tell the difference between the flat pieces or bulk pieces, we might need to add more images to that data set. And then we've got to move on to a Lego assembler X robot simulator, just so we can practice what it really looks like when the pieces can be assembled together. And then lastly, just updating our robot code so then it can pick up the Lego piece, but also be able to apply pressure to other Lego pieces so the assembly process can happen.
So during this project, we have quite a few people to thank. First and foremost, our faculty mentor, Dr. Yuhan, just because without him, none of this would be possible. We would like to thank our graduate mentor, Derrick, for not just the project, but giving us actual life and research advice. We would like to thank CEAMLS. We'd like to thank Dr. Mack. We would like to thank Michael and Elijah, the program info program coordinators, for always being available and keeping us on task. We would like to thank any guest presenters throughout the SAIRI program, and all those who work behind the scenes that don't quite get the credit that they deserve. And we would also like to thank you all, our fellow coworkers, who have motivated us throughout the summer.
We have about 4 minutes for questions from the audience. What would you say is the hardest part of making all this connected and getting to work? What was the hardest challenge? The hardest part of making the whole project work? Yeah. That has to be in the hardest part of this is the model itself. Once we're able to get like a good model and then we'll take out all of the bias and stuff and stuff like that, once we deploy the robots around, it's gonna be good.
And even just to add on to that, probably like when training the model, trying to see what are like the best parameters so we can get the best results, because we have to change things such as like the batch size, the image size, and just add other parameters that Abdulahi talked about with the HSV and just things of that sort. That would probably be part of our future work. We would hope that we can first begin with the simulator to make sure that it can do the full process without making mistakes, and then that will move on to the actual hardware where it also shouldn't make mistakes.
The robot should also be given a construction manual. We have a manual on giving Lego pieces, so we should make mistakes.
So what parameters do you think about when you put number of epochs? Okay, so one important thing is choosing a number of epochs. We have to make sure that the model was not overfitting, because that's what we're really worried about. But like 100 epochs was not sufficient, but so we have to increase to 150, and then we were kind of monitoring the results file was generating to make sure the model was not overfitting. So we're not trying to have like a super high epoch, because if you do that, it's going to memorize the image and it's not going to memorize the pattern. It's rather just the image.
So I have a question about, so were you guys actually able to achieve like real-time inference based on the accuracy?
Yeah.
So did you guys face any challenges in trying to kind of accelerate the hardware process? Because real-time inference is very
Accelerate the what?
So did you guys face any challenges in trying to get that real-time inference onto the hardware? Whether you hardware communication, specifically trying to get that real-time inference based on whether you should have been based on accuracy.
Oh yeah, there was a major trade-off we made in doing that. The major trade-off we had to make was the speed, was computational power of the hardware we had, and then the time it was going to take for it to build a Lego structure. So we had 11 as the best, 11 as the best overall, but the large model was much more accurate, but the small model was less accurate than large. But then we had to make the trade-off between the time and accuracy, because the small was not so bad. We had a recall of about 86%, a precision of about 86%. So it was decent enough, so that's what we did. We deployed on the robots on the NGI computer. We have to look at the trade-off, and then that's why we chose the model we chose. So it's going to cover up the speed at the time. So the larger model would have been much more accurate, but which requires much more computational power than the one we had.